When people talk about aligning a language model, they usually reach straight for reinforcement learning. And that works, but it is complicated and it can be unstable. So here's a simpler idea that captures a surprising amount of the same benefit. It powered part of the alignment behind Llama 2, and it goes by a few names. Rejection, sampling, fine-tuning, best-of-end distillation, or just RAFT. Today we walk through how it works and why it stays so stable. Really, this whole method is one loop that you repeat as the model gets better. Follow it once, and the idea clicks. Everything starts with sampling. For a single prompt, you ask the current model for many candidate answers, not just one. Maybe 8, maybe dozens. Because you're drawing from a distribution, some of those answers will land far better than others. And that spread is exactly what we are going to exploit. Next, every candidate gets scored. A reward model rates how good each answer is, or you use an automatic verifier when the task allows one. Did the code pass its tests? Is the math actually correct? That gives you an honest ranking of which attempts were strong and which were weak. Now comes the filtering step, and it is brutally simple. You keep only the best scoring answer or the top handful, and you throw the rest away. What remains is a small pile of high-quality responses that the model itself produced on its very best attempts. Nothing here is human-written. It is the model's own good work selected. Finally, you do ordinary supervised fine-tuning on those winners. Plain next token training on the answers that survive the filter. Then you take the improved model and run the whole loop again. So each round trains on cleaner, stronger examples than the last. So why bother with this when reinforcement learning already exists? Line the two approaches up side by side. Online reinforcement learning, something like PPO, is powerful, but it carries real weight. You need an on-policy training loop, careful reward shaping, and a lot of tuning to keep it from diverging. When it goes wrong, it can collapse in ways that are genuinely hard to debug, and the whole setup is heavy to stand up. Rejection sampling reduces all of that to 3 moves you already understand. Sample, filter, and fine-tune. There is no delicate policy gradient machinery. Nothing to diverge mid-training, just supervised learning on the model's own best outputs. You give up a little of what full reinforcement learning can reach, and in exchange you get something far more stable and easy to reason about. Strip the method down, and 3 ideas carry the entire thing. First, best-of-end sampling. You deliberately generate many answers per prompt so that the good outliers have a chance to appear. The more you sample, the better the top candidate tends to be. Second, reward-guided filtering. A reward model or a verifier decides which answers survive, so the training set is curated by quality rather than by chance, and low-quality attempts never reach the fine-tuning step. Third, plain supervised fine-tuning on the winners. No reinforcement learning at all. You simply teach the model to imitate its own best work, which is why the process stays so predictable and stable across rounds. All right, for takeaways worth keeping. Rejection sampling fine-tuning aligns a model by training it on its own best answers instead of running online reinforcement learning. Every round samples many candidates per prompt, scores them with a reward model or verifier, and keeps only the top ones. Because the final step is ordinary supervised fine-tuning, it stays far more stable and simpler than PPO, which is why Llama 2 used it. The trade of a little peak performance for a lot of stability is a pattern worth understanding. Plenty more AI methods get this same plain language treatment over at Standarity.com. Come take a look.